All right. You might have noticed I picked some kind of disgusting vectors there. Let's talk about the process before we do the problem. So to find a vector of whatever length that points in the same direction as some other vector, here's the idea. Here's our vector pointing here, like let's call this vector v. Let's pretend this is the vector v, and it's however long it is. It's probably pretty long, right? Because it's got some pretty big components. But the idea is always the same here. To find a vector that points in the same direction with whatever length you want, first normalize the vector you're given to make it a vector of length 1, and then multiply it by whatever length you want it to be, so it'll be a vector of length 10. Now, there's an additional thing we can do to make our lives suck less, which is I don't really want to do it for this, right? Because if I do it here, the magnitude of v is, right, it's the square root of 40 squared plus negative 75 squared plus 85 squared, which is terrible. It comes out to be, eh, I forget. Actually, I think I made a mistake, to be perfectly honest, which is totally fine. But here's something I want to point out. You're trying to vector the points in the same, you're trying to find a vector that points in the same direction as this vector. So you know what you could use instead? You could use any multiple of this vector. So instead of doing this terrible thing, I can see that all these components happen to be a multiple of 5. So I could just divide out the 5 first if I wanted to. So you could also say, I'm going to use this vector instead. W equal to, I think, what, 8. Negative 75 divided by 5 is negative 15. 85 divided by 5 is 17. And at least that's a little bit just less cumbersome to work with. These vectors, v and w, point in the same direction. And no matter which one you use, if you divide it by its magnitude, they're both going to point in the same direction and both have a length of 1. So if it's convenient, it's often useful to multiply a vector by any constant you want before you start trying to find some other unit vector for it. And this one I did kind of screw up the numbers. That's all right though. So that wasn't really the point. The magnitude of w here is the square root of 8 squared plus negative 15 squared plus 17 squared. Which, okay, is kind of gross. I admit it. I did mess up the numbers. I was going for something different. But that's going to equal the square root of 578. Or more nicely, 17 root 2. I know that because I picked the numbers especially because there is a Pythagorean. I was going for a Pythagorean triple, but I screwed it up. I was going for 8 squared plus 15 squared equals 17 squared, but I forgot that I was including too many components there. Still, we can still do the problem. So now we want two things. W divided by the magnitude of W is going to be, let's not make it too terrible. Let's be smart about it. It's 1 over the magnitude times the same vector. And then if you're trying to make it have length 10, multiply the whole thing by 10. So our unit vector is this. 10 times our unit vector is going to be 10 over 17 root 2 times 8 negative 15, 17. There's a vector that points in the same direction. It has to point in the same direction because it's a multiple of our original vector, and it has to have length 10 because it's a unit vector multiplied by 10. The next question is better because here, well, because the numbers are turned nicer, but here we can do the same sort of thing. Instead of finding the magnitude of this vector, make your life easier. Say, okay, instead of using, let's call this one, I don't know, let's call this R. Let's say that the vector S is root 17 times R, which is just a lovely 3 comma 4. And then S divided by the magnitude of S is going to be 3 comma 4 divided by, what's the magnitude of that vector? You've seen 3, 4 enough to know that the hypotenuse of that right triangle is 5. And so then if we want our vector of length 2 pointing in the same direction, 2 times S over the magnitude of S is going to be 2/5 times 3 comma 4. If you prefer, you can distribute and say it's 6/5 comma 8/5. You could have gotten the same result by doing the same work with this, but it's going to be really, really ugly because you're going to have to divide by like 5/17 or something. So if you're scaling a vector, it's perfectly legitimate to scale a scale of that. And sometimes really convenient to do so. Okay. The problem I was just doing made me think of that. So I thought it was worthwhile to look at that. Let's continue talking about the cross product. Let's actually remind ourselves of both the dot and the cross product, just just a reminder for if you've got vectors u and v, and let's say that u can also be written component wise as u1, comma u2, comma u3, and v is going to be written component wise as v1, comma v2, comma v3. Then u dotted with v, which is equal to v dotted with u, you can either think of as the length of u times the length of v times cosine of the angle between them. But you can also calculate this by multiplying the corresponding components together and adding up the results. So it's u1 times v1 plus u2 times v2 plus u3 times v3. And even though we are typically thinking of vectors that are 2 or 3-dimensional in this class, this idea has higher dimension analogs. You can do this for a 4-dimensional or a 5-dimensional or a 20-dimensional vector and still take the dot product by multiplying the corresponding components together and adding up the results. On the other hand, the cross product does not have higher dimensional analogs, or at least not that I'm aware of, but I'm pretty sure there are not. I'm moderately sure. I'm not pretty sure. I think there aren't, but I don't actually know because I haven't done explored it, but I don't think there are. So the cross product, u cross v, which is not equal to v cross u, but I will point out it is actually equal to negative v cross u. It is anti-symmetric. Sorry, anti-commutative. This next part we never really use except for when we need to. Which sounds, I know, kind of dumb, but okay. It's the magnitude of u times the magnitude of v times sine of the angle between the vectors multiplied by the vector n, where n is a unit vector that is perpendicular to both u and v. But really, that's not super useful if you're trying to actually calculate the dot product of two vectors, sorry, the cross product of two vectors. So there's a long way which you're almost never going to use. Not this. There's another. So there's two more calculations here for calculating a cross product. And yes, we are going to do it a long, terrible way kind of once, just so you can see how terrible it is. So I'll remind you last time that we found that looking at the XYZ coordinate system and the vectors, let me label things appropriately here. The unit vector I in the X direction, J in the Y direction, and K in the Z direction. Pen is not doing me any favors there. Sorry. Let's try that one instead. Much better. So last time we talked about how I cross J, well, by this definition, right, I cross J should equal the magnitude of I times the magnitude of J times sine of the angle between them, and sine of 90 degrees is 1, times a normal vector that is perpendicular to both of those vectors. But here's the question. Should it point upward in the z direction or downward in the z direction? Because both directions are perpendicular to both the vector pointing in the x direction and the vector pointing in the y direction. Or more generally, both of them are perpendicular to the xy plane, right? The plane that is spanned by those two vectors. I know that's maybe not a word you guys have heard yet, but you'll definitely hear it in 22A. So the way we answer that question is via the right-hand rule. So if you put your fingers along the direction of the first vector, so if you use your right hand, that's why it's called the right hand rule. Don't use your left hand. You use your right hand pointing in the direction of your first vector, in this case I, curl them towards J. Your thumb points in the direction that your perpendicular vector has to point to. So with I cross J, it's got to be in the positive K direction, which is just going to be K. On the other hand, if it was J cross I, it would also be 1 times 1 times 1 times, but now we're pointing in the downward direction because if you put your fingers in the J direction, and curl them toward your right hand again, curl them towards the x-axis in the I direction, your thumb points downwards in the negative K direction. Don't worry, it's not going to be super hard to do all this eventually. In the same sort of way, we said this last time, I'm going to say it again. It's true that J cross K is equal to I, K cross I is equal to J. And so then, of course, K cross J should be negative I, and I cross K should be negative J. So it's kind of interesting, in my opinion. Basically, like if you cross two vectors in the xy plane, you get a vector that's purely not in the xy plane. Kind of interesting. So then we could use this to do something terrible, to find a cross product of vectors that are less nice. For example, if we say let u equal 2i plus 3j and v equal, say, 5i plus 4j, we're going to find u cross v by using the, oh, sorry, you can't see any of that, sorry. Sorry, if u is 2i plus 3j and v is 5i plus 4j, we're going to find u cross v by essentially just distributing across the cross product because it does have a distributive property. So we're going to have 2i plus 3j crossed with 5i plus 4j. And we're just going to essentially FOIL it out. So that's going to be 2i cross 5i plus 2i cross 4j plus 3j cross 5i, sorry, plus 3j cross 4j. Oh, I forgot. What's I cross I? Let's look back at the definition. So if I do I cross I, that's going to be the magnitude of I times the magnitude of I times sine of the angle between I and I, which is 0 because the angle between the vector and itself is 0 and sine of 0 is 0. So any vector crossed with itself is going to be the 0 vector. Or just, no, the 0 vector is the right answer there because it is a vector still. Okay. So this part is just going to be 0 because I cross I is going to be 0. This part here is going to be 2 times 4 times I cross j, and we just said that I cross j was equal to k. This part here is going to be 3j cross 3 times 5 times j cross I. J cross I is negative k. And over here, we're going to get 3j cross 4j, which is 0 because it's j cross j. So we end up getting 8 minus 15, so negative 7k. That wasn't too heinous, actually. Like I've done worse things. But this is not generally like the nicest way to calculate a cross product of two vectors, especially if each of them had 3 components. So let's do it one more time because I feel like that didn't emphasize enough how terrible it could be. I want to make you really believe that it's going to be super terrible. So you'll really appreciate how much nicer it's going to be in a minute. So let's look at one more example. You might not want to write this down because it's going to get pretty gnarly. Let's say we have u equal to 2i plus 3j minus k and v equal to I minus 2j plus 3k. And now when we do the cross product of u cross v, oof. So it's going to be 2i plus 3j minus k cross I minus 2j plus 3k. So we're going to FOIL this out. We're going to get 9 things altogether. Let's be smart about this. So I'm going to get 2i cross I, which is going to be 2 times I cross I, plus 2i cross negative 2j, which is going to be minus 4 times I cross j. 2i with 3k is going to be 6 times I cross k. Oh my God, why did I do this? 3j with I is going to be 3 times j cross I. 3j with g, I should just write 0 there, but I'm not going to. Minus 6 times j cross j. And then 3j with 3k is going to be plus 9 times j cross k. We're almost there. Plus minus k times I, so minus k cross I. Minus k with minus 2j is plus 2 times k cross j. And finally, minus k with 3k is going to be minus 3k cross k. Now, we know some of these are 0 right off the bat. I cross I is 0. J cross k is 0. K cross k is 0. And then we're left with minus 4i cross j plus 3j cross I. But those are really essentially the same thing. That's going to give me a minus 4 times I cross j is k, plus 3 times j cross I is negative k. I don't remember which way did they go. They kind of go in alphabetical order. I with j gives you k, j with k circles back around to I, k circles back around with I to give you j. So if you think of it right, if you like kind of write it as like I, j, k back around, I cross j gives you k, j cross k gives you I, k cross I gives you j. And if you go backwards, you get negatives. It kind of works. Or you can draw the right-hand rule thing. I don't know. Really, you shouldn't do any of this because you don't have to in just a minute, I promise. We're almost there. So we dealt with that. Let's see. And then we have 6i cross k and minus k cross I. And we know that k cross I is j. So this is going to be plus 6 times minus j. And where'd the other one go? Right there. Minus another j. And then finally, the last one, j cross k. So we get 9 times I. And then k cross j is minus I. So we get 2 times minus I. All that to say, finally, we have, okay, negative 4k plus minus 3k is, let's actually write the other one. So 9 minus 2 is 7i. And then negative 6j minus j is minus 7j. And negative 4k plus 3 negative k is minus 7k. And I promise you I wasn't going for all sevens. I just happened to pick numbers that happened to come out this way. So, fun fact, if I was trying to find a unit vector in the direction of the cross product, because often we do, instead of dividing this by the square root of 7 squared plus 7 squared plus 7 squared, I would first divide the whole thing by 7 and then divide my I minus j minus k by the square root of 1 squared plus 1 squared plus 1 squared to make it much easier to normalize that vector if I was asked to. So, why did we do all this? So that now we can see how much better it is to do it the other way. So here's how we're actually going to calculate this thing. We're going to use what's called the determinant method for calculating the cross product. U cross V. And let's do the same example. So where U is equal to 2i plus 3j minus k, and V is equal to I minus 2j plus 3k. And we will pray that it did not make any errors here, so when we do it this way, it comes out the same, which is always a crapshoot. Sometimes a crapshoot. So here's what we're going to do. We're going to write a 3 by 3 matrix. So U cross V is going to equal the determinant of a 3 by 3 matrix. The first row is always I, J, K. The second row is going to be the coefficients of I, J, and K in your first vector. In this case, for U, it's going to be 2, 3, negative 1. And then the components of your second vector, V, 1, negative 2, 3. And before we get going too much further here, I probably should actually mention what a determinant is, because you might not all have known or seen what a determinant is ever. You might have, but you might not. So when you take 22A, you will definitely learn about matrices and determinants. But for now, here's what you need to know. Let me actually use a whole new piece of paper for this. I'll come back to this in a second, I promise. So for a 2 by 2 matrix, say A, B, C, D, the determinant of A, and I'll point out, so just so you know this, for matrix notation, we use brackets for the matrix. If you're writing the determinant of that matrix, you can either write it as det of the matrix, A, B, C, D. But a more common notation is to write it as essentially the same matrix, except you're writing just vertical lines as opposed to brackets there. It's kind of like an absolute value symbol, but it's the determinant symbol. But it's kind of like that because it does produce some numerical quantity. So when you take the determinant of a 2 by 2 matrix, it's going to be A times D minus B times C. For any larger square matrix, it's always going to boil back down to this. So for some larger matrix, like say, we almost always use A, even though I've already used A, I don't care. So let's look at this larger matrix. A, B, C, D, E, F, G, H, I. The idea for the determinant of a large matrix, now there is a shortcut for doing a 3 by 3 matrix. I don't think it's beneficial. Not because it's not good, but because you're going to have to do larger matrices anyway, and the shortcut is only good for 3 by 3s. I will mention it at the end, but here's how I really want you to think of this. We're going to use the method of what's called cofactor expansion, where you pick any row or any column. When you're taking linear algebra, pick the row or column with the most zeros in it. Here there aren't any zeros, so we're going to pick the first row. So pick the first row, and then for each entry in that row, here's what we do. So for the first entry, A, we multiply it by the matrix that's left, and you cross out everything every row and column that contains A. So when I cross out the row and column that contains A, I'm left with the determinant of the remaining 2 by 2 matrix, E, F, H, I. And so I'm going to have E, F, H, I. I'm going to leave myself a little space in front here because there's something I'm going to add on at the end. So then for B, leave some space in front of B if you're writing this down. I'm going to cross out the row and column that contain B. I'm left with the 2 by 2 matrix DFGI. And finally, for the last one, C, I'm going to cross out the row and column that contains C, and I'm going to get DEGH. The only other thing you need is to alternate signs. But really what's happening here, because I would like to be more general so that you actually know what's going on for when you take linear algebra, is that you're always multiplying by -1 to the power of the row plus column that you've picked. So A is in the first row and first column, so we're going to multiply by -1 to the 1 plus 1. And then every other entry, you're just going to add 1 to that. So for B here, it's in the first row, second column, you're going to multiply by -1 to the 1 plus 2. For C here, which is in the first row, third column, -1 to the 1 plus 3. The reason I'm mentioning this, though, is because if you pick the first row or first column, it's always going to be plus, minus, plus, minus, plus, minus, plus, minus for however many entries you have. Because the first row, first column, 1 plus 1 is always going to be 2, and -1 squared is always going to be 1. But if you happen to be doing this and picking a different row or column, like, say, the second column, because there's a lot of zeros there, which is convenient for later on, you're going to multiply by -1 to the 1 plus 2, which is -1 cubed, which is -1. So your alternating signs start off with a negative instead of a positive. Not going to be an issue for this class, because we're always going to be picking the first row, but I just want to save you some thinking later on. Like, oh, not that you shouldn't think about this, but like now you can kind of know why you're getting a negative or a positive to start because of where we are starting this process. Okay. And then I don't really want to multiply this out, but I'll point out that this is A times EI minus FH. This is minus B times DI minus FG. And this is plus C times dH minus EJ. EG. I'll say two more things. Thing one, hopefully you can see that you could extend this idea to any square matrix. Because if it was a 4x4 matrix, you would just use a row or a column and expand along that row and have remaining 3x3 matrices. And for each of those four 3x3 matrices, you would do this and expand along a row or a column and get three 2x2 matrices for each. Right? It's gross, which is why you want to look for a row or a column that has a lot of zeros, because if you have 0 times a bunch of stuff here, you don't have to think about that. So when you're doing this later on, when you take 22A and a quarter or two, pick the rows or columns that have the most zeros. Okay, the other thing I want to say here is that specifically for a 3x3 matrix, there is a shortcut. And the shortcut is the following. So here's the shortcut that you can use. You write your matrix A, B, C, D, E, F, G, H, I, and you either copy the first row and second row below it or the first column and second row, column to the right of it. So A, D, G, B, E, H. And then what you do is you multiply these things together this way. So you're going to have A times E times I plus B times F times G plus C times D times H. And then you do the opposite thing going the other way. So minus that times that times that, that times that times that, that times that times that. So it's going to be minus CEG minus AFH minus BDI. And if you compare this to that, you should see all the same things. I have an AEI, I have an AEI. I have a negative AFH, I have a negative AFH. I have a negative BDI, I have a negative BDI. I have a positive BFG, I have a my G turned into a J somehow because I don't know why. I have a positive BFG. I have a positive CDH, I have a positive CDH, I have a negative CEG, I have a negative CEG. They're the same. So this trick for taking the determinant of a 3x3 matrix can be used if you find it convenient. It's not my favorite, though. I feel like it's just as easy to write out this personally. So back to the problem we were doing. We're going to find the determinant of this matrix very, very fast by saying it's going to be I times the determinant of the 2x2, 3, -1, -2, 3, minus J times the determinant of the 2x2, 2, -1, 1, 3, plus K times the determinant of the 2x2, 2, 3, 1, -2. And hopefully these are all 7 or -7. So let's see, we end up getting I times 9 minus 2 minus J times 6 minus minus 1 plus K times -4 minus 3, which ends up being 7I minus 7J minus 7K. Is that the same? I better hope so. It is the same. Okay. Thank goodness. Much better than the thing we did before to calculate it, in my opinion. So when you're finding the cross product of two vectors, this is how you should do it. You should put IJK. Now do make sure that you put the components of your first vector in the second row and your components of the second vector in the bottom row. I will just show you here real quickly. If we did V cross U, which is going to be same sort of thing, IJK, but now it's 1, -2, 3, 2, 3, -1. We calculate that, we end up getting I times, let's see, we have the -2, 3, 3, -1, minus J times 1, 3, 2, -1, plus K times 1, -2, 2, 3. Well, it kind of makes sense if you switch the rows, right? Because that's all these are. This and this are just the same, but the rows are switched. Same with this, same with that. Then you're going to essentially change the order of subtraction. So here we're going to get I times 2 minus 9 instead of 9 minus 2. And here we're going to get minus J times -1 minus 6 instead of 6 minus -1. And here we're going to get plus K times 3 minus -4 instead of -4 minus 3. So you end up getting exactly -7I plus 7J plus 7k. So now you really can actually see that the cross product is anti-commutative. If you cross product in the opposite direction or order, you get the negative of what you would have gotten. Cool. So what do we do with all this? Good question. What do we do with all this? Lots of things. Um, yeah, okay, sure. So there are lots of fun things to do with this. So one example is the following. Let me not go too fast here. Yeah, sure. Okay. Sorry, things are going away fast. There they go. Bye. So here's an example. Find a vector perpendicular to the plane 3x plus y minus 2z equal to 12. Okay. So, well, we need to find a vector perpendicular to the plane, but we only need to know how to find like vectors perpendicular to other vectors. So what do? We look at the plane and we find some vectors in the plane. Let me show you what I mean. So if I draw this plane, which I've maybe poorly picked something here, that's fine. So here's my x, my y, my z. So let's see, my x-intercept would be 4. My y-intercept would be 12. My z-intercept would be -6. So the plane looks kind of like this. And I'm trying to find a vector that's essentially kind of pointing out, right, and down that is perpendicular to my plane. Well, if I want to find a vector that's perpendicular to a plane, I need two vectors in that plane so I can take their cross product and find something perpendicular to it. So I have a lot of points in this plane. I bet I can find some vectors in this plane. I've got the point 0, 12, 0. I've got the point 4, 0, 0. And I've got the point 0, 0, -6. Pick any two vectors. Essentially, I'm going to start maybe here and end there. So one of my vectors, let's call that one v. The vector v is, well, if I'm starting here and ending there, it's going to be 0 minus 4, 12 minus 0, and 0 minus 0. And it is a good idea, although not absolutely necessary, but it's a good idea to pick the other vector emanating from the same point. So let's call that vector u, and u is going to equal, let's see, from there to there, so 0 minus 4, and 0 minus 0, and -6 minus 0. And the way I've drawn that vector, that's a good question. The way I've drawn my perpendicular vector, would that be obtained by doing u cross v or v cross u? Good question. Here's the way I'm thinking. Well, I'm thinking about literally putting my fingers, let's see, so I put my fingers across along v and then try to curl towards u. I can go that way. I think I'm pointing backwards. Whereas if I put them along u and curl towards v, I think my thumb is pointing out towards u. So I think that the one I draw looks more like u cross v than v cross u. Not a super duper important point, but just something I want to point out. So let's do u cross v. So u cross v is going to equal the determinant of this matrix, ijk, -4, 0, 6, -6, sorry, and then -4, 12, 0. So we're going to end up getting, let's see, I times the determinant of 0, -6, 12, 0, minus j times the determinant of -4, -6, -4, 0, and finally plus k times the determinant of -4, 0, -4, 12. Let's see. So when we do this, we get I times 0 minus -72, so 72i, okay, minus j times 0 minus 24, so -24, and then plus k times -48 minus 0. So then we end up getting 72i plus 24j minus 48k. Now, let's reduce this just a little bit because we don't really care that, like, we just care about the direction. We don't really care about the scale here. So I can divide each of these numbers by 12, more than 12 by 24, actually. If I divide by 24, 72 divided by 24 is 3. 24 divided by 24 is 1. And negative 48 divided by 24 is negative 2. And that vector is normal or perpendicular to my plane. And here is something that is not a coincidence at all. Those coefficients match those coefficients. That is not a coincidence. That is a guarantee that if you're trying to find a vector that is normal or perpendicular to a plane, you don't have to do any of this work. You can just look at the plane equation and say, cool, my I component must be the coefficient of x, my j component must be the coefficient of y, and my z component must be, or my k component must be the coefficient of z. That is a true thing. So, for any plane, ax plus by plus cz equal to d, a normal vector is the vector ABC, which is kind of cool. So, some examples of things. What time? Oh, I got time. So, an easy question. Feels almost silly to write it. Find a vector perpendicular to the plane 5x minus 17y plus 9z equal to 1. Well, cool, you already know it. You already know two good answers, probably, actually. So one answer would be the vector 5 comma negative 17 comma 9, or you could do the opposite of everything, or negative 5 comma positive 17 comma negative 9. Or really any multiple of those vectors, as long as it's not the zero vector. Here's a more interesting question. Find the equation of the plane containing the point three comma two comma 1 and normal or perpendicular to the vector n equal to 2i plus 3j minus 4k. Okay, well, great. We already know most of the equation of the plane. Right? We know if the normal vector is 2i plus 3j minus 4k, then we know that the coefficient of x is 2, the coefficient of y is 3, and the coefficient of z is negative 4. There's kind of two ways to do this. Here's kind of the easy way. We already know most of everything. We know it's going to be 2 times x plus 3 times y minus 4 times z equal to some constant. Let's call it d. And then all we're going to do is we're going to plug in these points, or I should say this point, singular, to find the value of that constant d. So I now plug in the fact that the point 3 comma 2 comma 1 has to satisfy this plane equation. You're going to have 2 times 3 plus 3 times 2 minus 4 times 1 equal to your constant d, which is going to be 6 plus 6 minus 4, which is 8. So the equation is going to be 2x plus 3y minus 4z equal to 8. Or you can do it the way the book does it, which is also good and actually does show something. So the idea here is the following. You're trying to find the equation of this plane. And you know that this vector is normal to it. And also this plane contains the point 3 comma 2 comma 1. It doesn't just contain that point, though. It contains lots of points. So the idea is any other point, XYZ, in the plane. Well, let me ask you all a question. What can you tell me about the vector from the point 3, 2, 1 in the plane to the point XYZ in the plane and the normal vector to the plane? Are those vectors perpendicular to each other? Yeah, they have to be, right? If that vector is perpendicular, if the normal vector is perpendicular to the entire plane, it's perpendicular to any vector that is in that plane, right? You might draw like this vector over here and be like, well, is it? But then you just slide it over, still pointing in the same direction to the point of normalcy. And then you're like, yeah, of course it is. So here's the way, this is actually not bad to do it. This vector here, let's call it V. And the vector V is the vector with components x minus 3, y minus 2, and z minus 1. Okay, this vector and that vector are perpendicular to each other. So what do we know about their dot product? Dot product is 0. So that's an important thing. We always want to be like, oh yeah, if you ever are saying vectors are perpendicular to each other, you should automatically be thinking the dot product is 0. And vice versa. If you're saying the dot product of two vectors is 0, like, oh, those vectors are perpendicular to each other. Or normal or orthogonal. Those are all words we use to kind of mean the same thing. So here, we're going to say that n dotted with v has to equal 0. But n dotted with v, well, we're just going to do it the usual way. We're going to multiply the components together. So it's going to be 2 times x minus 3 plus 3 times y minus 2 minus 4 times z minus 1 equal to 0. And if we re-express this, we have 2x minus 6 plus 3y minus 6 minus 4z plus 4 equal to 0. That's going to be 2x plus 3y minus 4z. Minus 6 plus 4 is minus 8. And if we add it over to the other side, it's the same equation. And this is really kind of shows why it works. Why the coefficients of your normal vector have to be, or I should say the components of your normal vector have to be the coefficients of x, y, and z. Because they're literally getting multiplied together when you do the dot product of these things that has to equal 0. It's kind of neat. All right. How much time do we have? I got 5 more minutes. Okay. Should we? Yeah, we should talk about that, I guess. Sure. So, one thing I'll mention here, probably not today, and definitely not today. Maybe next class or the class after, we're going to start talking about some formulas for distances between things. And here's what I will say now, and I'll say again later. Most of these are going to involve an angle between some two vectors. And basically, most formulas are going to boil down to, is it helpful to use sine of the angle or cosine of the angle? If it's cosine of the angle, we're going to use the dot product because the dot product has cosine in it. If it's sine of the angle, we're going to use the cross product because the cross product has sine in it. I'll say that again, but I just wanted to kind of set that up for you. That's at least that's how I think of a lot of these. Is I'm trying to find some distance formula between two things. I'm trying to think of which trig function, sine or cosine, I need to use, and then use the appropriate dot or cross product to help me get there. If it sounds weird, it is a little weird, but don't worry, it's not going to be that bad. But we're not there yet. So there's a couple just like geometry formulas that we talk about here because they're kind of useful. So let's say we have a parallelogram. The area of a parallelogram. Well, let's draw it. So here's my parallelogram. Make sure I draw the lines parallel. And let's say, so I'll point out, right? There's my height. There's my base. And the area, very generically, is equal to the base times the height. But if we introduce some vectors, let's see what we can do here. So if we call this vector here, starting at A and ending at B, let's call that vector V. So the base really has a length of the magnitude of V. And let's call this vector that starts at A and ends at C, let's call that vector W. W might be a poor choice. Let's call it U. Sorry. There's another formula that uses UV and W, so I should probably try to be similar to the text here. So U is not the height. I should say the length of U is not the height. But if we use trigonometry, call the angle between V and U theta, I can find the height by saying that sine of theta is equal to the opposite over the hypotenuse, which is h over the magnitude of U. So then the magnitude of U times sine of theta is equal to the length of h, or the height. So our height's going to be the magnitude of U times sine of theta. And you know what? That looks a whole lot like the cross product formula, except we're missing the unit vector out here. So this is actually equal to the magnitude of V cross U. Because I'll remind you that if you were just calculating V cross U, it would be exactly this: the magnitude of V times the magnitude of U times sine of the angle between them times the normal vector that points in the right direction. I should say the normal unit vector of length 1. So if finding the magnitude of this whole thing, it would just be this magnitude times 1, which is just that right there. So basically, when you're finding the magnitude of a cross product, you kind of just ignore like the direction it points in. So there's a cross product that tells you a thing about a thing. Is it super useful? I don't think so, but maybe it is, and I just don't know. I will say you can also then find the area of the triangle ABC, which would be, this triangle here. It would be 1/2 base times height, which would be 1/2 the magnitude of the cross product. And that comes up kind of. Again, not a whole lot. Unless you're, I feel it, to me, this feels like a very contrived kind of thing, right? Like, here's a thing you can kind of do with the cross product. It's kind of neat. I'll stop there because